Thank you all for coming. The first note is that this session is eligible for AIA learning credits, 2 hours worth of credits available. If you would like to receive those, please email info@wcapt.org with your name, contact information, and your AIA membership number, and we'll make sure that those credits are given to you. We have 2 WCAPT announcements to make before the presentation starts. That is, the first one, we have an upcoming election to fill 6 board positions, including 3 new seats. We will be sending out an email notice shortly, but if anybody here would like to nominate themselves or somebody else, we are accepting nominations up until June 10th. And again, you can send those nominations to info@wcapt.org. And there's more information available on our website, wcapt.org. The new board members will be announced at our AGM, which is scheduled for September 24th. The election is to be held on September 10th. And with the AGM in mind, we have a save the date for everybody. This is the first announcement of our AGM, which will be on September 24th. The theme is restoration, rehabilitation, and reopening of historic theatres. Jim Regal, one of our board members, will be hosting the event with presentations from our 3 member states, that is California, Arizona, and Nevada. Keynote presentation will be from Broadway West. That should be very interesting, and we're looking forward to that. More details to follow. So for today's presentation, if you have any questions throughout the presentation, feel free to enter them in the chat box. John, Christina, and Maria will go through those at the end of the session and answer as many as they can. And after that, we will unmute everybody, and you're welcome to enter into a general chat until we end the meeting. We have John, Christina, and Maria here, excellent speakers with an excellent subject. I'm going to give them a short introduction, and then I will let them take over, and we'll get into the presentation. So John Fiedler is a British licensed architect with 2 postgraduate degrees in building conservation and over 40 years specialist experience in preserving historic buildings, ancient monuments, and archaeological sites. He is the president of John Fiedler Preservation Technology, Inc., an award-winning international consultancy based in Los Angeles. Previously, he was Conservation Director of English Heritage and Vice President at ECROM in Rome. Recent projects include the stabilization of the 1769 ruined plantation house of Menokin in Warsaw, Virginia, consulting on repairs to the 1690 gateways to Dublin Castle, Ireland, and brick and terracotta repairs to the 1915 First Congregational Church of Long Beach. He is currently rewriting the late Sir Bernard Fielding's Conservation of Historic Buildings for its 4th edition. Maria Mohammed is a project engineer at Structural Focus. She holds an MS in structural engineering from the University of Southern California. Maria is a licensed professional engineer with experience in structural analysis, design, and construction administration for existing and new structures. She has worked on significant projects, including Google's Los Angeles headquarters and the renovations of the John Anson Ford Amphitheater and CBRE Masonic Temple. Maria was named Young Engineer of the Year in 2018 by the Structural Engineers Association of Southern California. Christina Varvey is a Senior Conservator of Rosa Lowinger & Associates and Professional Associate of the AIC. She holds an MS in Historic Preservation with a concentration in Materials Conservation from Columbia University's Graduate School of Architecture, Planning and Preservation. A specialist in architectural and public art conservation, Christina is RLA's lead professional for all projects west of the Mississippi River, including Hawaii and Alaska. She is a specialist in modern architectural materials such as linoleum and synthetic finishes, outdoor sculpture planning, treatment and surveys, as well as large-scale mosaics conservation and architecture surveys, testing, treatment, and specification development. So with that, John, if you'd like to take control and take it away.
Thank you, Alan. I hope everyone can see this. Let me know if you can't. Welcome everybody, and thank you for attending today. We've got friends and relations and colleagues from all around the country attending, so you're all very welcome. I'm going to talk about saving the Streamline Moderne, the conservation of stonework and the gold glass mosaic at the what is now called the Saban Building, the former May Company department store in Fairfax and Wilshire in Los Angeles. I'm going to speak for a little while, and then my colleagues will come in on their parts of the exercise. You've all, I think, seen this learning objectives. What I should say is don't try any of this at home. Whoops. Got my, there we go. So for those of you who are unfamiliar with the site, the Academy Museum of Motion Pictures is along the Miracle Mile at the West End and adjacent to the Los Angeles County Museum, LACMA, and other museums there on Wilshire. And you can see it bounded by the red line. This aerial photograph taken during the course of the works. Of course, the works are now more or less complete, and our work actually took place a little earlier. But the opening of the museum has been taking a long while in gestation, not only because of various reorganizations of the museum, but also because of the need to fit out the exhibitions for the spaces, and then the COVID pandemic has slowed down that work even further. So the museum is now destined to open officially on the 20th September this year. But the gestation, as you'll see, goes back over a long period of time. And our particular work was actually completed in the spring of 2019. However, since all the other consultants working on the site, and in particular Gensler, the architects, Buro Happold, the engineers, and Matt Construction, the general contractor, have been using their publicity machines recently to focus on the design and the construction of this museum, and demonstrating lots of video links and walkthroughs via YouTube and LinkedIn. We thought it would be appropriate to remind everyone about the conservation work that went on to the 1939 May Company building that you see here in the bottom two photographs. We did present some of this information, first of all, at a California Preservation Foundation lecture we presented way back in 2018. The Academy Museum has long been in the minds of the Academy of Motion Pictures, and eventually they were able to persuade Renzo Piano to take on the job. And you see one of his famous doodles here at top left, and then the concept of the design in the cross section you can see here. The space between the former departmental store and the great theaters that are in his raised globe respects a long line of public pathways that walk through the site up to the La Brea tar pits, and he wanted that to be stressed and preserved. There's some very clever engineering work in the new design, that's to be admitted. This great globe, this concrete-clad edifice is sitting on 4 piers that rock in earthquakes. The escape towers you can see bottom left in the CG image are actually hung from the structure, not supported from the ground. The bridges from the globe into the older building can move in 3 dimensions in order to be stable during earthquakes. So some very fancy and sophisticated work involved in the new design. And what we hope we can show this afternoon is we were equally ingenious over the design of the retention, repair, stabilization of the cladding systems for the historic building itself. We're talking about the Streamline Moderne period. The building was finished in 1939. And you can see here some of the precedents for that work in the work of the futurists, the Soviet constructivists, and lots of nautical and aerodynamic motives coming through in design, marine design issues coming out of the Queen Mary, which of course is now in Long Beach, and other buildings that you can find along the Miracle Mile and elsewhere too. That is essentially rounded corners, projecting metal balconies, long ribbons of windows, and so on. It's good to remind ourselves that this part of Los Angeles was in fact agricultural grounds and a series of oil fields back in the 1920s. And it wasn't really until the 1930s that development was taking place here rapidly in the development of suburbs. And so it was that the May Company wanted to produce an out-of-town flagship design for its stores. It had one already in downtown LA. And this May Company store here at Fairfax in Wilshire, and a primary location of gateway to the Miracle Mile, was specifically designed to attract motorists as they drove in and out of town, and was surrounded by car parks. As Maria will explain, it's a steel frame, mass concrete, reinforced concrete structure clad in various kinds of stone. In the 1980s, the site was threatened with demolition, saved by a massive campaign by our friends at the Los Angeles Conservancy, locally listed as a cultural historical monument, and some due diligence repairs took place, which I'll come back to later, and the site was ultimately transferred to the Academy Museum Foundation in 2012. Previous to that, there was a proposal for 3 large skyscraper tower blocks to be on this site. A.C. Martin was the architect, but he did the work in association with the store architect, Samuel Marks, who worked for the May Company and others at the time. I know someone on this call said that they used to go and shop here. Well, unfortunately, all these brilliant historic interiors are sadly lost. Many of them had disappeared by the time the May Company devolved itself of the site. Others disappeared during the LACMA period, and more or less just bare naked concrete was left by the time that Renzo Piano's scheme came into being. Of course, the building has been studied and investigated over a long period of time, and I show here on this slide the chronology of some of the reports made by various firms locally and from further afield. Many of them, because of limitations of time and cost, were limited in their outlook. But as time progressed, more and more intensive investigation took place. And I believe the work by Wisgeny and by Simpson, Gumpers and Hager, SGH in particular, helped to understand some of the problems of the facade, although not in as much detail as we were fortunately able to generate. By the time we arrived on the site as a team, work was underway on the foundations of the new building. There was hardly any roofs left on this building. All the glazing had been removed. So the building was open to wind and weather in various directions. And the cladding was seen and perceived to be in a very bad state indeed. The organization of the project team is interesting. None of the parties involved in the new build design or their overall responsibility for the project as a whole, and that included Gensler and Renzo Piano for the adaptation and reuse of the May Company building itself, none of them wanted to have responsibility for the cladding system. Gensler and its consultants had advised the Academy Museum that it would be far more prudent to demolish the existing cladding systems on the building and replace them in new, if necessary, to match existing, to please the planners. But the Academy took a different view. The first director of the museum said, well, the May Company building is the biggest artifact in our collection. It should be preserved in the way that we would address artifacts in the museum's collection. And so Paratus Group, who were the project managers, I think the second or third set of project managers on this project, asked around. They had worked on, notably on the renovations and repairs to the Guggenheim Museum in New York, and inquired of the chief conservator for the Guggenheim as to who he thought might be able to provide a conservative type of approach to the cladding. And I was nominated and was lucky to obtain the job. And here's my team in this diagram here: structural focus for the engineering, Driscoll Studio as architectural consultants and support, GBG for metric surveys, E2 Chen for corrosion engineering, and Rosa Lowinger Associates for architectural conservation. We were directly responsible to the client through the project managers, not through the architectural line, although we had a very collaborative association with Gensler, Renzo Piano, and Mac Construction, and ultimately worked together to provide the ultimate response. Mac Construction and I conferred on the subcontractors for the actual carrying out of repairs, and I suggested Western Specialty for their knowledge of waterproofing and masonry conservation on the West Coast. And Mac Construction found Premier Tile to deal with the mosaic because conservators, architectural conservators, were not allowed on this job as contracting entities because of a trade union, city, county labor agreement over the project. Everyone had to be union staff. At my interview, I was able to tell the management group that I did indeed have a conservative line on repairs. If it ain't broke, I don't want to fix it. And I pointed to pictures of Tom Hanks as examples. Mr. Hanks is a trustee of the Academy Museum, and I pulled out these pictures of from his yearbook, and as he is today, and told the board that I wasn't interested in Hollywood facelifts. The building would look old when I'd finished with it, but it would be intact and alive. When we got to grips with the interior of the building and started to look at, in particular, the A.C. Martin's characteristic window boxes, steel welded boxes attached to the reinforced concrete with steel window frames, we could see that there was a degree of corrosion, but it was not as spectacularly aggressive or worrying as had previously been foretold. We can see here in the cross-section from his blueprint drawings, which we were fortunate to have, that there were various anomalies where water would be able to get in, particularly if in construction at the beginning of the project, some of the details had not been effectively aligned. And we were able, therefore, top right, to find corrosion in the bottom of window jambs in the frames caused by essentially the plasterers from the inside of the building. Instead of taking their rubbish out, they dumped it into the frames before they were sealed, and so embedded a lot of water holding materials where there should have been drainage or no water at all. So we were able to use simple repair techniques, minor pieces of arc welding, the use of epoxy metal putties, and the rest, once the frames had been abated, to then make those repairs. For the cladding itself, which is Texas Cordova Shelly limestone. It has the appearance of travertine, but it's not geologically formed in the same way. This stuff comes from about 40 miles northeast of Austin, Texas. We saw patterns developed in the masonry. This is stack bonded materials, which are 48 inches wide, 68 inches tall, 3 inches thick, applied over a 1 inch of cementitious type S grout onto the 16 inches or 10 inches of reinforced concrete behind. We saw these characteristic patterns, these linear spalls at the top or bottom of runs of the material, and then in side joints, corroding dowels. In investigations, we were able to remove some of these panels and found shelf angles and kerf anchors which had corroded because the drainage for the system lacked flashings and the water ran backwards onto the shelves and caused corrosion. We noticed too that the corrosion and damage was only taking place where these metal parts had not been previously lead painted. Certain elements and certain parts of the building, notably the west elevation, was less damaged than the east, perhaps an indication of different teams working at different times on the elevations. So recognizing that there were these forms of decay and deterioration, but they were not everywhere, we decided that a bespoke, custom-directed repair strategy was going to be best, that we didn't need to take much of the masonry off the elevation, provided we could hold the bulk of the cladding in place and then address the bottom and tops and some of the sides of the material in part. And I was not the first to think about using a pinning system for this technique. I believe that Gensler had consulted our local contractor specialist friends, Spectra, and they had suggested this too. Nevertheless, you may know the Helifix dry fix anchors, these helical friction anchors, were invented by the Brits, by the Helifix company in South Wales. And so I was familiar with their operation, but not with their potential structurally in a situation like this in a seismic zone. So our concept was to pin the bulk of the cladding panels in situ, cut off the offending spalls top and bottom, and then apply Dutchman after we'd carried out repairs to the substrate. Of course, key to all of this was getting a fix on the specific damage to each individual panel, and there were over 1,200 of these panels on the building. The client could not at that moment in time justify the use of scaffolding on the elevation, and the Fairfax-Wiltshire junction is one of the busiest for traffic in the country, and therefore the city was not going to allow us to use cherry pickers out of the street in a hurry. And speed was of the essence, we were told. So we deployed GBG US Limited. Actually, Al carried out the work when he was working for GBG. And we used the Gigapan technology here, which is a hyper close range telephoto lens camera, capturing very high resolution raw images. The system is automated so that you point it top left, bottom right of an elevation and let it rip. And then you mosaic together those images and you can look at them in very, very close detail. So for example, we could look at flies scratching their back of their heads on window ledges, that sort of thing. Other kinds of technique that had already been applied to the site were of no use at all. There was an existing laser scan, but it was insufficiently detailed for a masonry assessment of this kind. A bosun's chair, swing stage, or rope access would have been too slow to get the amount of information we needed to get in a hurry. Having got that information from these photographs, we were able to put them onto schedules, and then each individual stone could be assessed for its bedding plane, as depending on which way the orientation of the beds are in the stone, they'll decay in different formats, and then work up the repair specifications per panel. Here's the helifix-dryfix asymmetrical helical anchors that we used. They taper from 8 to 6 millimeter, the smaller diameter biting harder into the reinforced concrete at the back of the wall system. We had Helifix's agents come and produce some demonstration tests for us. Pull-out tests were supplied, and Structural Focus will talk about the results of that work. It showed a lot of promise, but we needed more information about the stone. So we commissioned a batch of material tests from a series of manufacturers, chemical and petrographic analysis of the mortars and grouts by Sandbergs in England, who I've always used for my mortar testing over the centuries I've been working in this field. And then in Pleasantville, New York, John Walsh at Material Testing, a Highbridge Material Testing Consultants, actually looked at the performance of this very strange micritic limestone sand. Limestone. It performs in very odd ways. It actually shrinks slightly when it gets wet, whereas most stones expand. And it has a coefficient of thermal expansion less than the ubiquitous Indiana limestone. So that gave us some confidence about how this material might perform when we looked at it in more detail. And I'm going to hand this over to Maria, and she's going to tell me when to move the slides.
Thank you, John. So like John mentioned, the historic May Company building was constructed in 1939, and it is designated by City of LA as a Streamline Moderne structure. Next slide, please. This is a historic photo of the building during construction that really captures the true structural makeup of the building. When you look at the building, it appears to be a concrete building, but it's actually a steel framed building. It's supported by steel beams and steel columns, and there is concrete slab that spans between the steel beams, and there's also an infill concrete wall between the steel columns along the perimeter of the building. On the interior, when you look at the columns, they look like they're concrete columns because they are encased in concrete, and the concrete basically was used as fireproofing with minimal reinforcing around it. Next slide, please. The main facade consists of limestone panels, like John mentioned, and the connection of the limestone panels to the exterior building wall is typically, as you see in this slide. There are steel curve angles that are cast into the concrete wall with cast in place anchors. And the limestone panels sit on top of the shelf angles, and there are curves that extend into the thickness of the limestone panels. These limestone panels are about 4 feet wide by 5 feet tall. They're mostly 3 inches thick, and they weigh about 800 to 900 pounds each. So these are big pieces of stone throughout the exterior of the building. And there is 1 inch of mortar backing behind the limestone panels. And during some of the initial assessment of the existing facade, there was tapping tests done by, I believe, SGH that found that there is some delamination between the mortar, the backing mortar, and the limestone panels. So for all intents and purposes, the support and strength of the limestone panels was fully coming from the steel shelf angles. Next slide, please. So the connection between the limestone panels wasn't really watertight. So moisture was getting into the shelf angles, and the shelf angles were corroding and expanding. And as the steel kept expanding, it basically resulted in the limestone panels popping off along the edges of the panels. As you can see, this is a very typical condition around the window boxes where there is a line of spalled limestone panel, or there is a line of cracked limestone panel that basically follows the edges. These, structurally speaking, basically meant the restraint from the steel angle, the curve that extended into the limestone panels was lost because the piece of limestone that was going to resist any out of plane motion of the panels has either delaminated or has fallen off. So seeing that the condition was this severe, it was structurally imperative that the limestone panels were retrofitted. Next, please. So the overall retrofit of the building was done following the requirements of the California Historic Building Code by Buro Happold. So we also used the requirements of the California Historic Building Code for the facade retrofit. There is a section in the California Historic Building Code that I'm sharing on the screen right now, specific for non-structural features. And if a non-structural feature, which also includes exterior veneers and decorations, if any of those pieces result in a falling hazard and becomes a life safety hazard, it needs to be evaluated and it needs to be retrofitted through proper anchorage. So we used the requirements and the loading criteria of the California Historic Building Code section 8-7 to determine to what extent do we retrofit the connection of the limestone panels to the existing exterior concrete walls. Next, please. So like John mentioned, we used helical anchors for the retrofit of the limestone panels to the concrete wall. These are asymmetrical helical anchors. They are 6 to 8 millimeters in diameter, excuse me. And the thicker part of the anchor is in the limestone, and the thinner part of the anchor is in the concrete, since the density and the bond with the concrete is much larger than the bond with the limestone panels. And all of these are stainless steel anchors, and they were also installed with the intention that they will be countersunk from the surface of the limestone panel upon final installation. Next slide, please. So Helifix anchors have never been used for seismic retrofit of exterior facade in city of LA before. So we worked with the city's research department to basically determine what will be the capacity of these helical anchors when they are installed into the limestone panels. We worked with a testing company called Specialized Testing Incorporated, and we followed the requirements of ASTM E488, which determines the testing requirements for anchors that are embedded into concrete. So we had to test both the shear and tensile capacity of the helical anchors, and we had to test them in such a way that it mimics the true loading condition of the helical anchors once they are installed, meaning that the tensile force that we would apply on the limestone would mimic an out of plane loading from seismic excitation or wind, and the shear load we would apply on the anchor will mimic the gravity load that the anchor has to resist in supporting the weight of the limestone panels. And this was a picture that was taken during one of the shear tests. And you can see that we cast concrete following the same material properties of the existing exterior wall, pre-cracked the concrete to mimic true cracked concrete behavior, and also used the minimum amount of reinforcing that exists in the existing exterior wall. Next slide, please. So helical anchors don't really have a head. So it wasn't like we had the opportunity to grab onto the anchor and just pull it out of the installed position. So we basically had to place a concrete wall, place a membrane that prevents the limestone from bonding to the concrete wall, since we weren't relying on the existing mortar bed, and put the limestone, then install the helical anchors, but move the limestone in such a way that it disconnects from the assembly or detaches from the assembly. And specialized testing came up with this very creative scheme to do that test. They fabricated a steel shoe that the limestone panel was placed into. And there was a hole in the steel shoe for the helical anchor to basically go through and connect directly to the concrete wall. So the only connection between the limestone panel and the concrete wall in this assembly was just the helical anchor. So when we are sliding left and right the limestone panel by pushing or pulling on the steel shoe, we're basically mimicking shear loading on the helical anchors. And when we're applying a tensile load by pulling the limestone panel off of the concrete wall, we're mimicking an out-of-plane loading of tensile force on the helical anchors. Next slide, please. This is a close-up of the assembly during one of the shear testing. As you can see on the limestone panel, there is an X mark that indicates the location of the installed helical anchor. And basically the load is being applied through the jack you see to the side that is pushing on the steel shoe that is currently holding the limestone panel. So the existing limestone panels at the building consisted of two types of limestone panels, cross-cut and vein cut. So we did various combination of the tests to determine which type of stone would give us the least amount of capacity, both for shear and tension. So we did quite a few of these tests, and we used 16-inch by 16-inch limestone panels. And we also used 8-inch by 8-inch limestone panels. And the size of the limestone panels was determined based on how much edge distance we think we were able to achieve within the existing limestone panels at the building. So those tested for the 16-inch panels basically assumed an 8-inch edge distance, and those tested within that 8-inch panel assumed a 4-inch edge distance. But later on, we found out that edge distance didn't really matter. Next slide, please. So this is a picture of the anchor from that same test from the previous slide. You can see that the failure mechanism was just the helical anchor bending. And you can see there is a lot of localized crushing in the bond between the limestone and the helical anchors. And the anchors didn't really move within the concrete wall. All the failure was just limited exclusively to the bond between the limestone panel and the helical anchor. Next slide, please. So as we were going through the testing mechanism, as well as even preparing the testing procedure, we were in contact with the city of LA to make sure we were in line with what they would like to see to justify the capacity for these anchors. So we tested both, like I mentioned, vein cut and cross cut panels, and we tested both in shear and in tension. And when we calculated the coefficients of variation for the number of tests we did, it was more than 15%, which is a number that the city usually likes to see. So we concluded that it will be best to use the lowest measured capacity from all of our tests. So we basically picked the lowest measured capacity for crosscut panels in shear and crosscut panels in tension, and also took the lowest measured capacity for vein cut panels in tension. And we agreed with the city to apply a factor of safety of 4 on these lowest measured capacities, and came up with a design capacity for each anchor of about 90 pounds for crosscut panels and 132 pounds for vein cut panels. And we used these capacities to basically determine what would be the total number of helical anchors we will need to install in a single limestone panel to properly attach it to the exterior concrete wall. Next slide, please. So in order to produce construction documents, we had to verify which one of the existing panels are crosscut and which one are vein cut, since the anchor capacity varies between those two types of panels. So we produced this elevation. John Fiedler and Driscoll were very, very helpful in producing this, and color coordinated to indicate which panels are crosscut and vein cut. And we also had to indicate which panels had gravity support, which meant we didn't need to provide gravity support for the anchors, and which needed new gravity support. So the ones that needed new gravity support basically were the ones that had the shelf angle cut off, because the shelf angle was extremely damaged. And that basically meant the panels near the window boxes all had to be supported for gravity as well as for out of plane. And once we indicated the types of the existing panels, we produced elevation views that showed pinning patterns. And we determined the pinning patterns in combination with the number of anchors we needed to resist the 800 to 900 pound weight of the stone and the seismic load of the stone, as well as the edge distances that we were able to accommodate and the spacing we were able to accommodate. And we also showed the helical pattern required for the new Dutchmen that were installed above the window boxes, and also along any of the limestone panels that had spalled corners. And once all the elevations, it's okay, John, you can move to the next one. And once all the elevations were put together, we ended up pinning about 1,200 limestone panels altogether. The installation for the helical anchors actually went pretty fast. It only required pilot holes to be drilled, and immediately followed with the helical anchors, and it was just a very smooth installation process. Once they knew where the anchors needed to go, it was pretty fast to get them in there. Next slide, please. This is the final installed configuration of one of the limestone panels. This is actually a panel that had a Dutchman replacement. So you see the new panel joints at the top and bottom on the left-hand side. And you can see a zoomed in picture of what the helical anchor looks like once it's installed and countersunk. So unless you know a specific pattern to look for and you are standing right next to the limestone panels, you really will not be able to see that there are helical anchors installed into the limestone panel facade. And standing from the street, looking up a few floors up, you really won't be able to tell that there is a pattern of limestone anchors and helical anchors installed into the limestone panels. because the holes just blend in really well with the natural holes and shell indentations of the limestone panels.
Thanks, Maria.
You're welcome.
So you'll have grasped from the elevational drawing that the lines of spalls were at the window box heads where there was a lack of adequate waterproofing. And when we had the panels pinned and removed the sections where there were spalls in the photograph on the left-hand side, you can actually see that in fact, the window box configuration actually drains backwards towards the angle of the wall there. And, you know, we'd lost more or less all the back of the window box and some of the supports at that location. And because this was the most common decay phenomenon in the building, we decided on a uniform height for the Dutchman repair for spalls in these locations, and to produce, therefore, a continuous waterproof flashing up the concrete and onto the window boxes, then install a parge where there had been grout, and then the Dutchman in front of that, supported on mortar joints at the bottom, and then a tight junction with epoxy resin to the original host stone, which was still in situ, and therefore to produce an absolutely waterproof and water-resistant throw for water in the future. And we tried very hard with the contractor and with the stone supplier down in Texas to be able to match the bedding plane of the stone and the cross-cut or vein-cut patterns, textures of the material with the host panels wherever we could. The new stone arrived pretty damp from all the processing at the plant there in Texas, and was a little orange to start off with, but that's disappeared as time has gone on. And bottom right, you can see there is a line of Dutchman repairs there, and not many of them are actually showing particularly strongly in the elevational appearance. I have to say, during this whole process from concept to implementation, we consulted regularly with the Office of Historic Preservation, the Historic Resources team down at City Hall, and from the very start wanted their view on whether they were more interested in A.C. Martin's design concept or in material preservation. And we got a heavy hint that they wouldn't mind seeing more of the original material kept if it was possible. And so we worked in tandem there to generate this kind of response. At the southwest corner of the building is what are called pylons on the original drawings, with this extraordinary bridge structure surmounted over this extraordinary gold glass mosaic hemicylinder. And we wanted to get a grip on the condition of this granite at the same time as we were looking at the limestone. Same kind of gigapan surveys were carried out. And when we got scaffolding up around this area, it became evident that there was something else going on here. There were 220 granite panels, originally a specified black diamond granite from Escondido down near San Diego, but that quarry had been won out in the 1940s. About 80% of the panels were cracked at corroding anchor systems, but there was something else going on. 40 of the panels were curiously non-matching geologically and in color. They were brown in appearance. And you can see some of the deterioration here in these photographs. You can see that there had been some previous repairs, not very elegantly carried out, with new stainless steel anchors concealed by black-colored silicon sealant. There were also various holes cut in the in the granite for electrical power supply to what was the May Company signage that was originally neon illuminated on the two pylons. But this color differentiation was a bit of a puzzle. Maria very kindly offered to go down to City Hall archives to look at permits. Although the permits had been identified by the historians in a previous historic structures report, not sure anyone looked at them in detail or understood some of the consequences of what was in the paperwork. While me and the rest of the team had Weston remove one of the granite panels, and that was a bit of a shock. We found that the new brown panels were actually sort of bathroom scale, very thin section of material, 3/4 of an inch instead of 2.5 inch thick pieces of granite. They had a 3x1 marble liner adhered badly to the back with an epoxy resin that was already embrittling and falling away. Inverted stainless steel angles had been placed on the fabric, and then the liners were supposed to sit on or close to these angles, but there was a lot of padding in the way. And most of all, the replaced panels, these inferior replaced panels, were held on the building with bits of 3/16 inch wire, much of it corroding, and only tagged into head mortar dabs, not even attached to the concrete at all. So it turns out that in 1991, $200,000 worth of repairs have been completed by folks, we guess, before LACMA took over the site, by the May Company as it surrendered the property. Most of these panels have been taken off and reinstalled, not to the engineer's design and without a city permit. So they were shoddy, insubstantial, and non-compliant with the seismic retrofit code of the time. So regretfully, we had to say to the owners that although we dearly wanted to preserve as much historical fabric as possible, this lot was a turkey and had to come off and get replaced. We worked with Cold Spring Granite out in Minnesota, found their Raven Noir was a pretty good match for the material, and then Cold Spring used its own design construct. Designers, California licensed engineers to produce a curved anchor system to our overall performance specification, putting new panels back in replacement of these old ones. And that was finished off then by caulking with Dow 795 sealant backer rods, the whole wax. And all the while, we were starting to worry about the gold glass mosaic. It was pretty clear there'd been previous bad repairs. Christina will describe all of this. There were cracks in various places. And at the bottom of the hemicylinder, which you can't see behind the hoarding here in the map photograph, is a light well in which there were floodlights to bottom light the whole of the this great feature. Some people argue that the May Company wanted this ensemble here with the pylons to look like a woman's perfume bottle that would be sold in the store. Others remark that it looks like a pile of gold coins for Hollywood. But whatever its design, things were starting to fail. Tessera from the mosaic was filling the bottom of the floodlight well at the bottom of this elevation, and things were needed to fix it. And Rosa Lowinger, Associates, was one of the members of my team, and Christina will describe what they did next.
Thank you. I think you can go to the next slide, please. Okay, so like the limestone and granite cladding, the mosaic clad hemicylinder is original to the construction of the building. As you can see, it consists of a smooth poured in place concrete surface with horizontal bands that bump out from the structural surface. These bands are 22 inches high and extend about 3¼ inches from the surface of the hemicylinder. They're formed using ferrous reinforcement that's embedded into the structural concrete. Originally, there were no expansion joints, and a sloped parge coat was added to the top horizontal surfaces to shed water. And at some point, the parges were painted gold. There are over 300,000 individual tiles across the surface, with each tile measuring approximately 1 inch square. The vertical faces and horizontal undersides of each band are clad with tiles. They're affixed to the surface with a neat cement paste. Material analysis by other firms of the neat paste indicated that it's composed of normal to well-hydrated particles of Portland cement with a high abundance of belite and ferrite cement grains. There are trace amounts of very fine-grained quartz sand in the neat paste layer, and it's been deemed highly alkaline, which will feature later. The original grout is sanded, containing fine aggregate of natural sand, primarily quartz. The grout paste is also normal to well-hydrated particles of white Portland cement with a low amount of ferrite. The material examination, also performed by others, showed that it was extensively carbonated, that there's a high amount of trapped air voids, and that there were both horizontal and vertical microcracks throughout. So that's a little background on what we were dealing with when coming into this project. But before going into the details of the treatment, I wanted to give you some background on the tiles themselves, which will shed some light on the modes of deterioration we were seeing and how our treatments were informed. Next slide, please. The original tiles were fabricated in Italy by Orsoni, which has been manufacturing glass mosaic tiles in Venice, Italy since 1888. They were originally and still are primarily made by hand and consist of 3 layers. The first layer produced is the surface of the tile, which is fabricated from hand-blown glass. The craftspeople blow out long cylinders or balloons, maybe about a 32nd of an inch thick, which are then cut down into smaller square plates, about 4 inches square. The plates have a slight curve or cupping to them from being formed from this blown glass. And after they're cut, they're stacked and ready to receive the gold leaf. Next slide, please. Next, the craftspeople take the individual glass plates and run them over a small valve that's producing steam. They then use the condensation that's left on the convex side of the glass to hold the gold leaf on the surface. The gold leaf on the original tiles is 24 karat gold from India. Today, using different alloys of metallic leaf and colored glass, Orsoni can produce over 38 different shades of metallic leaf and glass tiles, which you see around the edges of the sample board in the slide there. And the interior tesserae are just their stock colored glass samples. Next slide, please. After the gold's been applied, the craftspeople take the thin gold-clad plates and put them glass side down, gold side up onto a circular wheel. They then take a blob of molten glass from the adjacent furnace using an iron rod and place the molten glass directly onto the plates. As this wheel turns, it goes under a roller, which simultaneously helps meld the 3 layers together, as well as provide a uniform thickness to the pie that comes out on the other side. And then the pies are then flipped over and laid out flat before being put onto a conveyor belt to be annealed and relieve the residual internal stresses. Next slide, please. After this, they're scored on the surface using measuring forks to determine the size. They're then broken by hand using small hand tools and modified machines. So between the hand-blown glass surfaces and the hand cutting of the tiles, this gives each individual one a unique shape and surface texture, which impacts how light is reflected off of the surface. They're then face mounted to sheets of paper with water-soluble adhesive and spaced according to the client's specifications. Next slide, please. So that brings us back to the May Company building. This most recent intervention wasn't the first or only treatment campaign, as John alluded to. We know for certain that there were various structural and cosmetic repairs conducted in the late 1990s, as well as additional condition assessments, exploratory openings, laboratory testing, which I talked about, and a sounding survey of the facade as late as 2014 and 2016. So it was evident that the issues that we saw had been ongoing for some time. Our involvement began back in 2016 when we were contacted by John Fiedler. It was obvious from the street and canopy level that there were still a litany of issues going on within the hemicylinder, even after the 90s intervention, which we also knew from other firms' investigative findings. Next slide, please. As John mentioned, these conditions included networks of cracks, primarily through the grout lines, though also through some of the mosaic tiles. The most obvious cracks noted from afar were horizontal, some of which appeared to align with cold joints at the building floor levels. There were also patches where people had removed tiles to conduct investigative openings and just areas of tile loss as a whole. Next slide, please. There were also several campaigns of replacement tiles that didn't blend particularly well with the adjacent surfaces. These replacement tesserae were almost perfectly 1-inch square. Their edges were relatively straight and the corners at 90-degree angles. Also, the gold leaf utilized in these tiles didn't appear to match the color of the original gold leaf, and the surface was very flat, both of which caused the replacement tiles to reflect light differently than the originals, and thus they stood out in comparison. Next slide, please. As you can see here, the original tiles exhibited a wide range of surface conditions, depending on their location on the facade. The primary mode of deterioration was surface spalling and cracking, both through the thin glass faces as well as through the full body of individual tiles. The spalls mainly occurred between the thin glass faces and the gold leaf. Depending on how the damage occurred, the spalls would look opaque white or light pink with atmospheric soiling collecting in these cracks. In some instances, the glass had completely separated, leaving the gold leaf exposed. And in others, though less frequent, both the surface glass layer and gold leaf had detached, leaving the bright blue-green glass substrate exposed. Next slide, please. Located at the southwest corner of the building, the hemicylinder is subjected to strong UV throughout the day, particularly at the south side of the facade. There's no trees, there's building close by, but they don't cast shadows, and there's no architectural elements that mitigate the exposure of this element to direct sunlight. So it's subjected to large swings in temperature between daytime and overnight hours. And this is especially true in the summer and early fall, where the temperature differential between night and day can vary between 20 and 40 degrees Fahrenheit. In addition to thermal stresses, this area of the facade or the whole building is subjected to seismic activity. And furthermore, as John indicated, it's located at a very busy intersection that sees extensive amounts of vehicle traffic. So it's subjected to near constant vibrations from passing vehicles of various sizes and weights. And I think even now there's the Metro purple line, I think, is extending past right in front of the building. So since there were no expansion joints anywhere on this facade, we believe that the various thermal and vibration stresses over time primarily contributed to the deterioration of original and even replacement tiles. The worst, most concentrated areas of this type of damage were observed at the top 6 courses, protruding and recessed bands, as well as along the south or proper left side of the hemicylinder. Next slide, please. Additional issues included various degrees of surface soiling due to the high traffic nature of the intersection, as well as alkali attack of the surface glass layer along the borders and some faces of original tiles. And this presents as a haze or cloudiness of the glass and was likely caused by the highly alkaline setting mortar leaching onto the edges and surfaces of the tile over time. Next slide, please. Thanks. These were just the conditions that we could see from a distance without any scaffolding or swing stages. Because as John mentioned, before the facade was scaffolded, we utilized those high resolution gigapan images to try and map and quantify the different obvious modes of deterioration, safe for detachment. And these included the continuous cracking, cracked tesserae, replacements, spalls, and discoloration and lost tesserae. We used existing maps of areas of detachment from a 2016 sounding survey to flesh out our visual survey, and those obviously weren't initially verified in the field by us. So the next slide is the resulting images, which we broke out by comparison or for comparison. And from these images alone, we estimated that upwards of 50% of the surface was exhibiting some form of deterioration and might require replacement, and that 15 to 20% of the surface was exhibiting delamination, either between the tile and the mortar bed and or between the mortar bed and the substrate. In designing the treatment, we weren't trying to reinvent the wheel. For the most parts, the repairs were fairly straightforward. Damaged and visually incompatible tiles would be removed, cracks and areas of delamination stabilized, new tiles set and grouted. The key would be in making modifications to the installation that would not be visually intrusive, but enable movement of the tiled planes to relieve stresses, as well as visually integrate replacement tiles and grout that are brand new compared to the 80-year-old originals. Next tile, please. Prior to the scaffolding going up, we worked with John and Hagen Flynn tile distributors to try and find the best match for replacement tile. We sampled tiles from different parts of the world and had sent out samples of the original May Company tiles to assist with this matching process. But many companies used contemporary processes that I mentioned, and it just rendered the tiles too perfect and uniform, similar to what we had seen with the 90s replacement tiles. The edges were too straight and squared off. They were much thinner than those of the 1930 tiles, and the surfaces were too smooth, so the light reflectance wasn't scattered as much as the original undulating surfaces. And furthermore, many of the manufacturers could not get close enough to the original shade of gold. So ultimately, we all decided that Orsoni still produced the best match for replacement tiles. And even though their equipment had been somewhat updated and the tiles were a little more uniform than the originals, their product still came the closest to blending with the 1930s tiles. So we sent them tracings of the original tiles so they could give us a range of shapes and sizes and to determine the spacing between them to help facilitate their production, as well as the preparation of the placement of the tiles on those adhesive sheets. Next slide, please. To relieve the stresses from thermal expansion and vibration, others had recommended vertical expansion joints as well as horizontal, but we agreed with John and his design team that this would greatly impact the visual integrity of the facade and its very strong horizontal banding. And as such, the design team came up with the idea to introduce horizontal expansion joints at two major changes of plane between the flat surfaces and the protruding bands. So of the three main planes, at least one edge would be along a soft joint. And at these joints, a flexible sealant was inserted versus a cementitious or modified grout. And a quick note on the parge coat, though this wasn't included in our scope, it was generally found to be in good condition and didn't have to be removed. There were minor areas that required patching, but ultimately it was coated with an elastomeric paint as an additional waterproofing measure. And the gold color was carefully selected by the design team as it would ultimately be reflected on the gold tiles on the undersides of the protruding bands. And so when we did get to our cleaning tests, we did test all those products on this, the membrane and the paint to make sure it wouldn't get damaged during treatment. Next slide, please. So once the scaffolding went up, our team began an in-depth assessment of the entire mosaic surface. We used two different color adhesive dots to mark tiles for selective removal by the tile contractor. Original tiles that were damaged and could not be reused elsewhere were marked with orange dots. Later campaigns of replacement tiles were marked with orange dots with a black X, whether they were damaged or not because they were visually detracting. And then original tiles that were in good condition but had to be removed to facilitate a crack repair were marked with green dots for removal and reinstallation elsewhere. And we use these dots to also try and quantify how many replacement tiles would be needed, as well as looking ahead, anticipating additional tiles lost during select demolition, as well as attic stock for the client for any future repairs. Next slide, please. During this survey, we also sounded all surfaces and marked off the boundaries of areas of noted detachment using different color tape to distinguish between delamination between the tiles and mortar, as well as within the substrate. We could tell that based on the type of vibration and the sound when we're sounding the surface. We marked these areas as well as all visible cracks through grout and tile on a drawing of the facade, which was then turned into official drawings provided to the tile contractor. Next slide, please. Once the demolition began, we came back through behind the tile contractor and checked for additional cracking in the substrate that may have been obscured by the tile overlay, marking that for repair as well. Horizontal structure cracks were routed, injected with structural epoxy and patched with a modified cement patching mortar and then coated with a flexible elastomeric coating. To allow for those to act as natural movement joints. Superficial losses in the concrete substrate were also patched to even the surface out before setting tiles. And we also specified materials and processes, as well as instructed the contractor in injection grouting of the substrate for areas of delamination. Next slide, please. And once the substrate was repaired, the tile contractor began resetting the salvaged original and replacement tiles. We work with the design team to select a grout color after cleaning an area of grout on the original surfaces. As you can see, there's a noticeable difference between the color of the binder and the fine aggregate when the grout's viewed up close. However, from normal viewing distance, you can't really distinguish these color differences. So we were really looking for a commercially available product that gave the same perception of color, hue, and tone. And for warranty purposes, all of the mortar and grout products that were used were from the same manufacturer. Next slide, please. And once all the tiles were set and grouted and the sealant applied in the movement joints, the surface was given an overall general clean to remove any extant atmospheric soiling, grout residue, and other surface contaminants. We conducted several cleaning trials as well as instructed the cleaning contractors in application, concentration, dwell times, and tools for cleaning these surfaces, and then also provided oversight throughout that process. Next slide. Finally, the contractors attempted to reduce the effects of alkali attack on the affected original tiles. Early on in our involvement before the scaffolding was erected, we removed several tiles that were accessible from the canopy and that exhibited this haze around the edges. And we tested 2 different glass cleaning products meant to help mitigate the surface damage and wound up ultimately specifying this product called Winsol Clear, Crystal Clear 550, which had very promising results in the trials at our studio. And obviously this was a small sampling and the extent of the alkali damage varied across the surface of the mosaic. After the general surface cleaning, we did additional trials in the field to refine the treatment approach, dwell times, materials that could or could not be used in conjunction with the cleaning, like mildly abrasive pads, brushes, and things like that. And ultimately, it was determined that no more than 2 passes could be done over damaged surfaces. Otherwise, it would create secondary damage. So while it did help mitigate some of the haze and subsequent matteness of the surface, some of the damage around the very outer edges was far too gone to rectify with this specialty cleaning method. Next slide, please. So all in all, we think the replacements are a very good physical and visual match, and they blend well with the originals and will do so even more after they weather and age. Thank you.
Thanks, Christina. I might say that the general public was quite enthralled by all this work going on, for the most part without a shroud or a cover on the scaffolding. Some folks thought it was an art installation. There were red dots, then there were green dots, then there was gray when there was no tile, and then there was lots of tiles. So we got an art performance out of it as well. Finally, the northwest corner of the May Company building had previously a wing which was erected in 1946 and went due north. And you can see the scar there, which is outlined in red, when the extension, the 1946 extension was removed. And it was always the intention to restore the original 1939 corner to the building. The center range of the north elevation, in Renzo Piano's view, should be a new curtain wall system looking out on from the exhibition spaces and offices and restaurants and so on in the innards of the old building, across to the theaters in the new globe, over the bridges and across the passageway there. And prior to us arriving, there was some discussion about a design and some drawings they had from another firm of engineers to turn this corner and to align the elevations at the east and west end of the building with the curtain wall. And there'd clearly been a struggle to try and get this sharp radii turn on the corner in New Stone. So when we were appointed, we were asked to look at this in detail, and we decided that we would utilize a brand new shear wall, which was being added in this corner by Buro Happold, as a stiffening, seismic strengthening for the whole structure. And instead of attempting to apply a sort of rain screen cladding on lots of rails for new stonework here, which made it jut out even more away from its original position, we'd use traditional stainless steel shelf ankles and kerf anchors, but we would turn the corner in a much sharper radii by using stones which were eccentric in cross-section on plan. And this is an old technique which has been used many times in the 18th and 19th century. And in fact, we were able to check this before we acted on the east corner of the building, the northeast corner, where the stone is thicker at a change of plane. And so it starts off as a straight stone and then does a dramatic bend as it turns the corner. And that way we were able to produce a very sharp radii on plan for the corner construction here. These balconies, which were called smoking balconies originally and had a sort of an in-out door, and I suppose, you know, if you were desperate for a fag while you were buying a fur coat or something, you could pop out here and have a smoke. These were going to be completely ornamental, and we made that point very clearly to the permit office down at City Hall. And in fact, that was advantageous to us as designers, because the wonderful sort of ship's railing here of these balcony fronts had caused a lot of damage in its connection from the steel work into the concrete through the masonry with spalls and so on other elevations. And we determined here that since the doors were going to be steel shut, were not to be used, we would no longer call this a balcony, but we would call this ornamental ironwork. And there are now no connections between the vertical balusters and the wall. They're just connected by the posts into the reinforced concrete balcony pad itself. The stonework follows the original design. We were fortunate to get enough panels of the right dimensions to make this replica of the northwest corner. Previous designs for the whole recladding of this building had made the assumption that the original stone, or something quite like it, would be available in vast quantities to replace all 1,200 panels. But in fact, spending a couple of days on site with the quarry managers in Texas, they were able to tell me that because of bedding plane and other changes at the quarry faces now available in Texas, there's a very limited range of this material that can be won in the vein and cross-cut nature of these panels in these sizes. And so we were fortunate to be able to win enough stone to make these things work. The shear wall was coated with a weather barrier. Stainless steel angles were applied, and then new Texas limestone was put onto them. And again, Dowsil 795 sanded sealant was used for the joints. So in conclusion, we had been told right at the start of the project by the owners that they wanted the maximum amount of original material saved, little or no changes to the architectural design of AC Martin. They needed answers quickly and cheaply in order to keep up with the rest of the program. In fact, we were able to surpass all of those criteria. We finished a year early compared with the rest of the project. We saved 88.4% of the total surface area of the facades. We saved 95% of the Shelley limestone, 100% of the stainless steel, the steel window boxes. Sadly, only 51% of the granite could be retained, and only 65% of the gold glass mosaic. However, we won on everything else. We did the whole piece of work for around about $6 million, which isn't bad on a project which is now in total, including the exhibitions, about 483 million in total. And if anyone is interested, supply and fit of the 24-karat gold glass tesserae, each tile is worth $7. There's the project team for the work, including the foundation, the museum folks, project managers, my team, including Driscoll's studio. Unfortunately, Caitlin and Bob can't be with us tonight. Scott Pons provided facade engineering activities for me. Maria and her colleagues at Structural Focus, Christina and her colleagues at RLA Conservation, and a whole cast of characters. I hope that's been entertaining and informative, and that we've kept more or less to time, and we're available for any questions you might have.
Thank you, John. Thank you, Christina and Maria. That was a great presentation of an excellent project. There are a couple of questions coming up in the chat box, which I'll let you take on. Before that, I just wanted to announce again to everyone who arrived after the introduction that if you require AIA credits for this, there are 2 hours worth of credits available. Just email your name, contact information, and AIA membership number to info@wcapt.org. And with that, John, please take it away with the questions.
Thanks very much. I'm going to be looking over to one side here, reading the chat box. The first question is from Alan Merson. Is the expected seismic design performance of the new structure in the rear and the existing building to meet or exceed code? If the design performance of the new and existing buildings are different, why is there a difference? Let's deal with that one first. Maria, do you want to attempt an answer to that?
Yeah. So I'm not really sure about the performance of the new building. The performance of the existing building was to meet, I believe, collapse prevention in the historic building code, which basically goes up to 75% of the current building code. So it's, I believe both structures are designed to just meet existing building code. And the design of the new building is different from the design of the existing building because seismically there actually are 2 different buildings. The dome is on a base isolator and the seismic force is just, concentrated off of the base isolators. It is not connected to the existing building. The 2 bridges that connect the dome to the existing building, they are designed to slide during a seismic event. So there's no force transfer between the new building and the existing building.
Thank you, that's good. In fact, those 2 bridges move up, down, side to side, and in and out. So they're freely moving in those directions. And as I mentioned, the emergency escape stairs, which are an expression on the outside of the globe building, they are hung from the structure and have universal joints, so they too move according to the rest of the structure. Alan goes on. Why is the word academy spelt from the bottom to the top? Good point. The original May company lettering on the elevations with the in bronze sheet metal with neon were actually spelt in a way that's easier to read, I have to say. This was a decision by the museum and Pentagram, who are the graphic designers, and a lot of the architects didn't think it was a very good idea, I have to say. But that's showbiz, as they say in the movie world, and we've got to live with it. Alan says, are expected vibration issues from the subway construction or future daily subway operation? Well, the big hole in the ground is east of the Peterson Museum on the other side of the street. There are subsidence monitoring laser targets on the Saban Building on the east and west elevation principally, and a few on the south, which relate to the tunneling. But there's no expectation, I believe, by Buro Happold that this is going to be a significant issue for the running of the museum. The issues are going to be on the other side of the street, particularly. That's the question from there. What else? I can't see any more questions here. I got a couple of issues I wanted to bring up for the gang, though. Christina, we should say something about the relationship that had to go on with Premier Tile. My original vision was for you guys to actually do the assessments and then physically do the work. And then I mentioned this labor agreement that the city and the county have signed for big projects, and trade union rules apply everywhere. I think it's fair to say that Premier Tile had no experience of conservation work in tiling at all. Their usual stick is to tear stuff off and put stuff on, right?
Yes.
So do you want to explain a little about how how I ended up working with them. You did a lot of training in essence.
Yes, I believe they were brought in by Western specialty contractors, and the foreman that they had on the job and his supervisor were very sensitive to the fact that this was a restoration project. Their foreman had been working there for at least 40 years. And so we initially worked with him in all of the testing and the mock-ups, and then he would disseminate that information to his crew, with us checking in periodically for different quality control checks for very specific things like for injection grouting. It was just 2 people who did it so that they could maintain quality control and consistency throughout the entire surface. And even when tiling, I think they had maybe 4 or 5 maybe different guys who did the actual applications of the tile. They selected their best people. They kept those as the only ones who were doing the tile work. So yeah, they were very interested and really absorbed the information. They were very receptive to constructive criticism and critiques and making tweaks in the field. They were really flexible. And all in all, they did a good job. They made little tools to modify, how they apply tiles, and yeah, it was a good experience.
Yeah, I think they were fascinated by your Dremel kit, which is about, an eighth of the size of the mammoth tools they were using for the most. Yeah. Something else that was fascinating about the tile work is you and I spent a lot of time thinking about how we would ask for the materials to come to us from Orsoni, and we asked for paper-faced material because that's the classic way that conservators do it. But Premier, they were so nervous, they actually soaked away all the paper and put them on in individual tiles.
Yeah. I mean, we even went to the trouble of doing the tracings of the original configurations and the spacing. I mean, that was for our Sony to get the range of tile sizes because it was a little organic, but so that they could make the spacing so that they could just lay the sheets right onto the surface and not have to fiddle with them too much, except for areas where there were smaller cutouts, which they then could, in theory, just trim the sheets. But yeah, it was just something that they really weren't used to working with. And then just kind of went the far extreme side of we'll just get them all off and place them by hand. But they, again, modified the their tools and their processes to make sure that even though they were doing that, there is some slight undulation with mosaics always. They're not perfectly flat almost ever. But there was really no huge discrepancies between tile placement, even though they were literally doing each one by hand.
There's a question from Annie Lowe for Christina. How challenging was the removal of tiles? I noticed that in the photo that some stayed in place while other ones directly above were removed, and vice versa, of course. So, you identified tiles which sounded hollow or were pretty badly damaged and therefore were having to come away. But others were pretty rock solid, right? And they could just be isolated and left where they were.
Yeah, definitely. And early on, we were very specific about, okay, let's keep this little area here. But early on, it became very apparent that was just not a very efficient way for them to work. So, if there was maybe 3 or 4 tiles in a field that was almost exclusively going to be removed, we marked those as green and said, okay, yeah, take these out and we'll just redo the whole area. And there were some collateral damage areas that we didn't expect to come off. They weren't as well bonded and they did come off with their removal, but yeah, there were other areas where they were on there. So they did work with Dremel tools. The grout size ranged. You could generally get a Dremel tool in between them without nicking the tiles themselves. But yeah, they were very good. And they collected all the tiles that came off and they sorted them into different bins based on those, on the color coding. And they didn't get rid of anything, I don't believe, until the very end, until the museum signed off. And I think if that's still the plan, that you can, in theory, buy jewelry now or some kind of memento or cufflinks with pieces of the gold tile utilized in them. So
yeah, we scored. We weren't part of the US Green Building Council lead calculation system for this project, which Gensler was doing with its consultants. But I think we scored big to help that regime, because everything that came off from the gold, 24 karat gold glass tiles, everything was salvaged, broken pieces as well as whole ones. As Christina said, they were then sorted by Premier. So there's an attic stock for the museum for repairs if necessary. And I believe they're still in negotiations with designers about jewelry and other trinkets that are going to be sold in the shop for some of the remnants that we used. Christina and I also conferred on this project with one of the great mosaicist conservators in the world, Roberto Nardi, in Rome. And the museum was very nervous that we were all over here. The factory was in overseas. So Roberto visited the factory on our behalf to help with quality assurance. And as Christina mentioned, they don't make the glass anymore that anywhere in the world that we all would have loved to use there, which is, I think the Germans and the British call it cathedral glass. But it's got lots of bubbles in it and divots in the surface, and that when the gold's put on top and then the other glass, you get a series of very peculiar refractions from that system. Now most of the glass is very boringly flat, so in order to replicate some of the crinkly surface of the original material, we specified what's called gilt gold. That is with creases in the surface. So instead of just having a flat piece of gold leaf on the surface, you use a brush and you fold creases into the surface of the material. So you've got little rivulets if running across the gold leaf to give that different refractive surfaces there under the top sheet of glass.
Mm-hmm. And I showed that too. They changed the sizes back in one of those slides where they had the cutting fork. Those are adjustable, so they can score it whichever size and way that you need to.
And we did specify, I think, at least 1 or 2 millimeters thinner than the originals, because we wanted to give the tilers some play in the inwards and outwards placement of the material because of the deformations in the surfaces they were attaching to. Yeah, I had a question from Maria, which is my understanding is that Los Angeles Department of Building Safety has done away with its research department, or is in the process of doing so, Maria. So that means that in future, any new anchoring systems will have to have prior national testing, right?
That's correct.
This kind of custom testing is no longer going to be possible.
That's correct. So I would assume the manufacturers would have to do the material testing before the product can be specified on a project.
And that for one-off projects a long way from South Wales in England is something they may not invest in the future. Luckily for the friction anchors, the patents ran out, and now there are about 4 or 5 different US manufacturers producing.
Mm-hmm. We're actually using one on another project now for hollow clay tile. So there's a potential for use in other products as well.
Yeah. I think we've run out of questions or points to be raised.
I don't see any more. I was going to invite those who are too shy to type in the chat box to unmute themselves and turn their cameras on and enter into a general discussion and chat.
No one's asked about what goes on inside the museum. There's a shark, a well-known shark, which is hanging from a beam. It's already getting a bit dusty, I have to say. So I got to have a word with the facilities managers. The rooftop is going to be a terrace with a tea room, as the main company had it. There are going to be exhibits which change all the time, and then static exhibits about the Oscars themselves. There's several exhibits going in right now, and then there's going to be a change of those. A ground floor shop, a large restaurant on 2 floors. The ground floor of the former May Company building, the Saban Building, is going to be a sort of throughway open to anyone who wants to just pass through the site, technically during opening hours, and then you pay to go to the higher floors and the more precious exhibits on display. I should mention the sponsors for the May Company's restoration is the Saban family, who some of you may know who have had children in recent years. Mr. Saban is the guy that owns the Power Ranger franchise. He admitted at a previous meeting that he didn't give money to museums, but it was cheaper half the price, and his wife wanted to donate to education. So we were the beneficiaries of some of that. The development team of the museum, meanwhile, has been getting sponsored donors for each column within the building. The ones that Maria mentioned is the steel stanchions clad in concrete. They were actually very elegantly clad in board marked concrete, which is quite attractive. And the development office has been flogging those off metaphorically at $1 million a pop. And for those that haven't asked, Tom Hanks is a very nice man, and Whoopi Goldberg is not at all funny when she's talking about the budget.
Thank you all very much. And thank you to everyone for coming. A reminder that we are always looking for more presentations. If you have any ideas for a project or a technology that you would like to talk to that pertains to historic preservation, we'd love to hear about it and include it in one of our upcoming happy hours. Email address info@wcapt.org. Visit our website to see what's coming up. We will have an announcement coming out soon about our upcoming AGM. And also the nominations are open for our upcoming election. So if you or anyone you know should be on the board, let us know and we'll see what happens.
Very good. Thanks, Al. Thanks, everybody.
Thanks, everyone.
Bye-bye.
Bye.